Hi everyone, Mr. Boltri here bringing you video 4.6. We're going to talk about finding the center of mass of some more interesting objects. So first we're going to talk about a general approach about how we're going to solve these problems. Then we're going to go through two examples of how to solve problems of using that general approach. So in our last video, we talked about how to find the center of mass by doing the mass weighted average of all of the so we're going to take the mass and multiply by the position, and mass multiply by the position, mass multiply by the position, and then divide by the total mass. If we have sort of point particles, or we can take sort of some funkier objects and then squish them down into point particles and then apply this same methodology. But what if we have something that is so complicated that it has a bunch of point particles, like hundreds or thousands or millions of point particles, or an infinite number of point particles? So that's where our super handy dandy ... comes in. And so we can basically say like, oh, we can add as many of these point particles as we want, and then just divide by the total mass down here. Mass weighted average of the position divided by the total mass. So what's this going to look like for hundreds or thousands or millions of point particles is we are just basically going to sum up the mass times whatever small little, the position times whatever small little subset of mass that is. And then we're going to add all those up. And then we're going to also add up all the little small subsets of mass, which is going to give us the position times the little subset of mass divided by the mass total. Haven't really changed anything so far, except so what if we take an object and we split it into small little chunks of mass, and let's say that we split it into 10 chunks of mass. Let's say we take this water bottle and we split it into 10 little chunks. Or maybe we split it into 100 chunks or 1,000 chunks or 1,000,000 chunks, or we could actually split it into an infinite number of chunks. And if we split it into an infinite number of chunks, then that means that each little chunk of mass is going to it's going to be the limit as each chunk of mass approaches 0 kilograms, which is calculus, if you guys recognize this. So actually, maybe you might recognize this a little bit more. If we take the limit of the sum of all of these things, then this is actually the limit definition of an integral. Is because we are adding up an infinite number of infinitely small products of position and mass, of infinitely small mass that we're multiplying by position. So the limit as it approaches 0 is an integral. It's going to be an integral of all the positions with respect to the infinitely small amount of mass. And this equation is going to be really powerful, and it's going to be how we approach finding the center of mass of some of these weirder objects. So let's actually, this is kind of hypothetical. Let's look at an example. And example 1 is going to be finding the mass of this right triangular wooden block. It's just a regular child's toy. So it's going to have some dimensions. It's going to have a length and a width and a depth. And we are going to figure out the center of mass of this thing. We're going to focus on the x direction, but you could apply the same principles to the y direction. So I'm just going to give it a little turn just so we're looking at the side view. But just remember that this thing does have some depth. It does go back into the page. But this is the side view, and I'm going to make it small and put it over on the side so we can do some math over on the right. And actually, the only numbers that we're given are side lengths A and B. And then we can solve for the center of mass using only A and B, actually, surprisingly. And I'm going to show you how. So we're going to put this on a little coordinate plane with the bottom left corner at 0, 0, and then it'll go to a length of A and then a height of B, and it's nice and easy. This is all just problem setup. This would be stuff that you'd be given in the FRQ if this was an AP exam. So we're also told, very importantly, that we're trying to find the center of mass of a uniform triangle. And that word uniform is doing a lot of work here because it means that it has a constant density. And in example number 2, we're going to look at things that don't have constant density. But for the purposes of this problem, this triangle has a constant density. When the factory was making the wood block, they didn't like slip a hole in there or anything like that. So it has a constant density. So then we're going to use the formula that we just talked about, the adding up the mass weighted position of an infinite number of little tiny masses and then dividing by the total mass. But there is an issue here. But before we get to the issue, let's just talk about what that means. So we're going to basically take this triangle and we are going to break it into a bunch of tiny little chunks of mass. And you'll see here that I use sort of a center Riemann sum, but we know that we are going to make that chunk of mass infinitely small. So it's basically going to be a perfect representation of the height of the triangle right here, because it is going to be infinitely thin in terms of our chunk of mass. So speaking of infinitely thin, it's going to have a width of dx. And we're basically going to say as dx approaches 0, the dm approaches 0. The little chunk of width gets infinitely thin, so our little chunk of mass gets infinitely light, I guess. But it is going to have a height of y, a width of dx, a distance from 0 of x, and then don't forget it does have some thickness going back into the page of t. So these are all important characteristics of our little chunk of mass, of which we have an infinite number in our triangle. We are taking our triangle and slicing it up an infinite number of times. So important, let's talk about what it means to have constant density. You guys have probably heard of rho, or this little P-looking guy. He's called a rho, and that's called volumetric mass density. And that basically tells us the mass divided by the volume of this big triangle. But just so you know, this is probably how you've seen it before, but this equation actually has some important implications. That also means that the total mass divided by the total volume is going to give us the volumetric mass, the same rho, the same density number. And because it has a constant density, we can also therefore say that any little chunk of mass divided by the volume of that chunk of mass is going to give us that same density because of the idea that we're using constant density. So the issue with this equation up top, the reason why we can't just like plug in numbers and solve it is because we can't really integrate x with respect to mass. We can't integrate position with respect to mass. Those two things don't go together, so we can't do that integration. So we actually need to either substitute out the mass and substitute out the position and figure out the position in terms of the mass, or vice versa. We need to substitute out this dm and replace it with something that's in terms of dx. So that's what we're going to do now. And you'll notice in this equation, we have a dm. So I'm actually going to isolate this dm in the equation by multiplying both sides by dv. And then I'm going to get dm equals the rho, or the volumetric mass density, times a little chunk of volume dv. And you might be wondering, well, Mr. Boltri, how does this help us? Because we weren't given rho in the problem. We were only given a and b. Well, it might be necessary to solve for rho in terms of a and b. So actually, if we think about, before we do that, if we think about what is the volume of this little chunk, this little rectangle, what is its volume? We know volume is length times width times height. So it's going to be dx is my length, y is my height, and t is my depth, or whatever, a length times width times depth. So my dv I could actually represent as y times t, length times width times depth, dx. And you'll see now, aha, now we have something, we have a dm written in terms of dx, which is exactly what we wanted. So we could go ahead and substitute this in, but that wouldn't help us very much because, like I said earlier, we were not given rho in the problem. So we need to figure out rho in terms of the quantities we were given, which were a and b. In order to do that, I'm going to take this equation, put it over off to the side, and then use the other version of the volumetric mass density formula, which is the m total divided by v total. Now I can figure out the m total because that is something that we know. And then the volume total is just going to be 1/2 times base times height times the depth. So volume total is 1/2 times a times b times t. So you'll notice I'm just going to write capital M as M total. So I simplified it down at the bottom. I simplified it down here, so I can simplify it up here also, 1/m. And so now we have our rho in terms of quantities that we know, like A, B, T, and M. So then I can take this volumetric mass density, plug it back into my dm equation, which would look something like this. I can take my rho, put it right here, and then get, this is the volumetric mass density times the length times the width times the depth of my little volumetric segment. So that was a lot. Let me just sort of take a step back and review what I just did. So basically, we were trying to replace this dm with something that's in terms of dx, but before I do that, I want to make sure that everything in my quantity that I'm replacing is in terms of the variables that we were given in the problem, like x, y, t, a, and b. So that's kind of all we just did. And then I'm going to take this and then put it into my formula to replace the dm with all of this dx. And actually, I can clean some of this up before I do, because we have t in the numerator, t in the denominator. Dividing by 1/2 is the same as multiplying by 2. So I can take this and plug it in for dm, and then I get this equation. So then what I'm going to do is I'm going to actually factor everything out that does not vary in terms of x. So as x increases, the total mass stays the same. So I can pull out the 2 and the m. I can pull out the a and the b because those are constants in the problem. So the only thing that doesn't change in terms of x over the course of this, as x increases, is x, obviously. And also you'll notice the y value as x increases, y also increases. And you'll see the m's cancel, which is actually pretty convenient for the purposes of this problem. Okay, so we're almost there. We can almost integrate this. The only thing that we're missing is now we need to write this y in terms of x, and then we can integrate and solve. So to write the y in terms of x, we are going to think about similar triangles, which we can use the angle-angle postulate, because we know that this lower left angle is the same and they both have the right angle. So then we can set up our similar triangles. A over b equals x over y. Solve for that. Y is actually equal to b times x divided by a. Substitute that y into our integral equation. And again, we can take out things that don't vary in terms of x, which are b and a. So we get the x center of mass is located at 2 over a squared times, if we just integrate a whole bunch of little widths in x squared. So this is now a kind of very simple integral calculus problem where we can use the product rule of integration to solve. But the last thing that I want to do here is I want to add some bounds of integration. So we're going from 0 all the way up to a in terms of our x squared, which we know when we actually do that definite integral is x cubed over 3 from a to 0. Plug in a minus 0, and then we get, actually, the x center of mass is located at 2/3 a, which is about 2/3 of the way down the wood block, which makes sense because over here there's not as much mass, over here there's more mass, so it should be closer to the right than it is to the left. Okay, that was a whole lot of work to solve for only the x location of the center of mass of this wood block. But an AP would really love to see you do all this work for a FRQ problem. This would not be a multiple choice question, but you sort of need to understand at least the general premise of it in terms of how to find the center of mass of an irregular or a weird object such as this one. So for example, number 2, I'm not going to do it in this video because I'm already feeling like this video is long, but I will tell you all the setup and then we will do it in our next class. So the thing about example number 2 is that this object has a non-uniform density. So its density, we're actually given in the problem the linear mass density. So we know that the density of the object depends on how far it is down the x-axis. We're actually given a function for the linear mass density. So at x equals 0, has a density of 75 grams per meter, and it has a length of 0.9 meters. So sort of at 0.9 meters, it's going to have a density of quite a bit less than 75. It's going to be pretty close actually to 0. So as we move to the right, the rod keeps the same dimensions, but gets thinner and thinner and thinner in terms of it gets less and less and less dense as it goes on. So the question is, what is the horizontal center of mass of this rod? And I'm just going to give you a hint. It should probably be closer to the left than it is to the right, since it gets less and less and less dense as it goes on. So if you want to try this on your own, just sort of chew on this problem a little bit for yourself for 10 minutes or so, maybe even 5 minutes, just so we can come to our next class and then have some ideas as to how we're going to tackle this one together. But for now, this is Mr. Boltri wrapping up video 4.6, where we did some really cool calculus to find the center of mass of the objects. And for now, go Bears.